Hello everyone, welcome to Section 3, Data and Sampling. This chapter introduces the concept of a sample and explains how to extract samples effectively. In the previous chapter, we learned how to explore the apparent characteristics of data using visual charts and summary tables. These tools helped us identify patterns and difference in the data. However, the conclusions we drew at that stage were based mainly on observation and visual interpretation. While this approach is useful for initial exploration, it does not provide concrete evidence. To move beyond surface-level insights, we need to use statistical tools to formally examine the statistical properties of the data and support our conclusions with evidence. For example, when comparing sex and diagnosis, we observed that females appear to have a higher occurrence of meningioma, while males appear to have a higher occurrence of high-grade glioma. Based on this visual pattern, we suggested that there might be a relationship between sex and diagnosis. However, at this stage, this is only a hypothesis. The pattern could be influenced by random variation or sample imbalance. To confirm whether this relationship truly exists, we need statistical testing to determine whether the observed difference is statistically significant. Similarly, we observed that both females and males showed similar values for chi. From the visual comparison, we inferred that there might be no relationship between sex and chi. When examining a diagnosis and the gross tumor volume, we observed that different diagnoses appear to have different tumor volumes. This led us to believe that there might be a relationship between diagnosis and the gross tumor volume. However, these conclusions are both based on visual inspections rather than statistical proof. To establish whether these non-difference or difference are statistically meaningful, we must apply appropriate statistical methods. In the following two sections, we will focus on using statistical tools to test these relationships and determine whether the observed patterns have statistical significance rather than being the result of chance. In statistics, we often work with something called a sample and something called a population. A population does not always mean people or animals. Instead, it means the entire set of data that we are interested in studying. This population can be very large, theoretical, or even impossible to observe completely. Because we usually cannot collect data from the entire population, we take a sample. A sample is a smaller group of data points selected from the population. We then use this sample to learn about the characteristics of the population. You can think of this process through the idea of data and sampling distributions. The population is assumed to follow some underlying pattern, but we cannot see it directly. What we can see is the sample data and the distribution created by that sample. By using a proper sampling method, we can connect what we observe in the sample to what is happening in the population. In the past, statistics relied heavily on strong assumptions about the population. Today, modern statistical methods focus more on the sample itself and require fewer assumptions, allowing us to make reliable conclusions based on the data we actually observe. A sample is only useful if it truly represents the population. This means the sample should reflect the key characteristics of the larger group we want to study. One of the most important ways to achieve this is through random sampling. In random sampling, every member of the population has the same chance of being selected. When this rule is followed, we call the result a simple random sample. This approach helps reduce bias and makes our conclusions more reliable. A famous historical example shows why proper sampling matters more than sample size. In the 1936 United States presidential election, a magazine called Literary Digest surveyed more than 10 million people and predicted that Alf Landon would win. At the same time, George Gallup surveyed only about 2,000 people and correctly predicted that Franklin Roosevelt would win the election. The reason for this difference was not how many people were surveyed, but who was surveyed. Literary Digest used lists of subscribers and people who owned telephones or cars. These groups were wealthier and did not represent the general population. This caused sample bias, meaning the sample was systematically different from the population. When sampling bias exists, repeating the same flawed method will continue to produce incorrect results. And this example shows that how we select a sample is often more important than how large the sample is. Statistical bias means a systematic error that comes from how data is collected, measured, or analyzed. It is different from random error. Random error happens because of chance and does not push results in one specific direction. Bias, on the other hand, consistently pushes results in the same direction. This means the results are not just noisy, but actually misleading. A helpful way to understand bias is to imagine shooting at a target. In an unbiased situation, the shots do not always hit the center, but they are spread out evenly around it. There is randomness, but no clear pattern in any one direction. This kind of variation is normal and expected. In a biased situation, there is still randomness, but the shots tend to cluster away from the center. For example, they might consistently land in the upper right area of the target. This shows that something in the process is pushing the results off target in a systematic way. Bias can be obvious or hidden when results consistently differ from known values or reasonable expectations. This is often a sign of bias. Common causes include poor sampling methods, incorrect statistical models, or leaving out important variables. Identifying and reducing bias is essential for producing reliable and trustworthy statistical conclusions. To avoid the sample bias problem that caused the Literary Digest to make an incorrect prediction, George Gallup used more scientific sampling methods to make sure his sample truly represented the voting population. Today, many sampling techniques exist, but a random sampling is still the most important principle behind all of them. In real projects, random sampling is not always easy. Before we take a sample, we must clearly define the population we are sampling from. For example, if we want to create a customer profile for a pilot survey, we first need to decide who counts as a customer. Should we include customers who received refunds? Should we include internal test purchases or resellers? These decisions directly affect the population and therefore the quality of the sample. Once the population is clearly defined, we can apply random sampling. In Python, this is commonly done using the sample method in the pandas library. In your Google Drive IS372 folder, create a new folder called Section 3. Create a new Colab file. Don't forget to import required packages or libraries like pandas. Then go to Canvas to download the LC loan dataset we need in this section. In this example, we first load a loan dataset into a data frame. Then we check the basic structure of the dataset, such as the number of rows and columns. This helps us understand the size of the population we are working with. Next, we demonstrate two common random sampling approaches using the sample function. In the first case, we randomly select a fixed number of observations, such as 500 rows from the dataset. Each row has an equal chance of being selected, which helps reduce bias. In the second case, instead of choosing a fixed number, we sample a fixed proportion of the data, such as 70% of all rows. This is useful when we want to split data into training and testing sets. Both approaches follow the same core idea of random sampling. When done correctly, they help ensure that our sample reflects the overall population and supports reliable statistical analysis. When we sample data from a continuous flow, such as real-time transactions or website visitors, timing becomes important. People may behave differently in the morning versus the evening, or on the weekdays versus weekends. If we only collect data at one time period, the sample may not represent the full population accurately. One common way to improve representativeness is called stratified sampling. In this approach, we first divide the population into meaningful subgroups, called strata. Then we randomly select samples from each subgroup. And this helps ensure that important groups are not missed or underrepresented. For example, in political surveys, researchers often stratify the population by demographic groups such as race or ethnicity. By doing this, they make sure that smaller groups are included in the sample, even if they make up a smaller portion of the overall population. Stratified sampling is especially useful when we expect difference between groups and want more balanced and reliable results. Stratified sampling is used to make sure our sample reflects the structure of a categorical variable in the original dataset. First, we look at the frequency of each category, for example, the grade column. We can use the function cal_explore to calculate the probability of each grade. Let's say our dataset has 1,000 records, and the grade B makes up 30% of the data. If we want to take a 70% sample, we need 700 records in total. To preserve the proportions, 30% of 700, or 210 records, should be grade B. The same logic applies to other grades, like grade A or C. In Python, we split the dataset by each grade. Randomly sample 70% from each subgroup and then combine them back. This way, the final sample keeps the same distribution of grades as the original dataset, making it more representative. Do you remember the function cal_explore that we created from the last section to calculate the probability of each category for categorical variable? We can use this function to explore the frequency of grade. Then we can do these. First, we find the unique values in the grade column using the unique function. This gives us all the different categories like A, B, C, and so on. We store them in a variable called the categories and print them out to see what we have. Next, we create an empty data frame called stratified_sample_for loop. This will hold all the sampled rows after we do stratified sampling. And we then use a for loop to go through each category in our list of unique grades. And inside the loop, we first create a subgroup by selecting all rows in LC_loans where the grade matches the current category. This is done using the bracket notation with a condition. Once we have the subgroup, we randomly select 70% of its rows using the sample function with frac equals 0.7. This ensures that we are taking the correct proportion of records from each grade to preserve the original distribution. After sampling, we add the sampled rows to our empty data frame using the concat function. We use ignore_index equals true so that the row indices in the final data frame are reset, creating a clean continuous index. By the end of the loop, we have a stratified sample that keeps the grade proportion similar to the original data set. Next, we calculate the proportion of each grade in the original data set using a value underscore counts with normalize equal to true. This gives us the relative frequency or probability of each grade instead of just the counts. We then plot a bar chart to visualize these proportions. We create a figure and axis object using subplots and then call the plot bar function on the probability series. Finally, plotted.show displays the chart. We repeat the same process for the stratified sample. we calculate the grade proportions, plot them as a bar chart, and display the figure. Comparing the two charts, you can see that the stratified sample closely mirrors the original dataset in terms of the distribution of grades, which confirms that our stratified sampling worked as intended. There is another optimized way to write the Python code. First, we convert all the column names in the LC_loans data frame into a list using the columns attribute and the toList function. And this gives us a list of all the column names, which we store in the variable called column_list. Next, we perform stratified sampling using a more compact and optimized approach. We start by using the groupie function on the LC_loans data frame, grouping the data by the grade column. The group_keys equals false argument ensures that the resulting data frame does not add an extra hierarchical index from the grouping. Then we select all the columns from column_list and apply a lambda function. A lambda function in Python is a small anonymous function defined using the lambda keyword. It is a concise way to define a function without giving it a name. For example, if we write square equals lambda xx to the power of 2, it is the same as defining a normal function with def square x, return x squared. You can then call square with an argument to get the result. In our code, the lambda function is defined as lambda x sample frac equals 0.7, random_state equals 42. What this does is it takes each subgroup generated by group B and randomly selects 70% of its rows using the sample function. The random_state equals 42 ensures that the sampling is reproducible, so you will get the same random selection every time you run the code. If we were to write this lambda function as a regular function, it would look like this. We define a function called sampling that takes x as input. Sample 70% of the rows using x sample with frac equals 0.7 and a random_state equals 42 and then returns x. The lambda function allows us to do the same thing in a single, concise line. Finally, the apply function runs the lambda function on each subgroup, and the results are combined back into a single data frame called stratified_sample. This optimized code achieves the same result as the for loop we used earlier, but it is shorter, cleaner, and more efficient, especially for large datasets. Next, I want to explain the idea of a sampling distribution using a simple and a concrete example. First, let's start with the basic idea. A sampling distribution describes what happens when we take many samples from the same population and calculate a statistic, such as the mean, every time. Instead of looking at individual data points, we are now looking at the behavior of a statistic across repeated samples. This idea is the foundation of statistical inference because in real life, we almost never observe the entire population. Now let's walk through the process step by step. The first step is to define the population. In our example, the population consists of all individuals in a group, and we assume the true average height of this population is 130 centimeters. This population is usually large and not fully observable. The second step is to choose a fixed sample size. In our case, we choose a sample size of 5. And this means that every time we draw a sample, we randomly select 5 individuals from the population. The third step is to calculate the sample mean. Each time we draw 5 individuals, we compute their average height. For example, in one sample, the 5 heights might be 128, 132, 125, 134, and 131. We calculate the average of those 5 numbers and record that value. That a single number is one sample mean. The fourth step is to repeat this process many times. We do not stop after one sample. We repeat the same procedure again and again, always drawing 5 new individuals and calculating a new sample mean. In our example, we repeated this process 20 times, which gave us 20 different sample means. The fifth step is to create a distribution of these sample means. Instead of plotting individual heights, we now plot the 20 sample means on a frequency chart. When we do this, we start to see a pattern. Most of the sample means fall close to 130 centimeters, while values far away from 130 are rare. From this example, we can observe several important ideas. First, even though individual heights vary a lot, the average of the sample means is very close to the true population mean. This shows that sample means tend to target the population mean. Second, the variability of the sample means is much smaller than the variability of individual data points. This means averages are more stable than raw observations. Finally, if we increase the number of samples from 20 to thousands, the shape of this distribution would become smoother and resemble a bell curve. This happens even if the original population is not normally distributed, and this result is explained by the central limit theorem. In summary, the sampling distribution of the mean helps us understand how reliable sample averages are, how much they vary due to random sampling, and why we can use samples to make confident statements about an unknown population. From step 4, we can infer that the mean may vary with different random samples. This is called sampling variability. Sampling variability provides the foundation for making generalizations from a sample to a population. It allows for the calculation of key measures like standard errors and confidence intervals, which quantify the reliability of sample-based estimates. Before talking about standard error, it is helpful to briefly recall variance and standard deviation. Standard deviation describes how spread out individual data values are around the mean. It focuses on the variability within one dataset, such as how different students' heights are from each other. Now, when we move from individual data points to sampling distributions, we need a different concept. This is where standard error comes in. Standard error is a single number that summarizes how much the sample mean varies from sample to sample when we repeatedly draw samples from the same population. Think about the sampling distribution of the mean. Each time we draw a sample, we calculate a sample mean and a sample standard deviation. If we repeat this process many times, we get many different sample means. The average of these sample means is essentially the population mean. However, these sample means are not identical. They fluctuate around the population mean. The standard deviation of these sample means is called the standard error. It is very important not to confuse standard deviation and a standard error. Standard deviation tells us how the data itself is distributed, meaning how individuals vary around the mean. Standard error tells us how the mean is distributed, meaning how much the sample mean varies across different samples. In simple terms, standard deviation describes the spread of data, while standard error describes the uncertainty of the mean. We can estimate the standard error using a simple formula. The standard error equals the sample standard deviation divided by the square root of the sample size. This formula shows something very powerful. As the sample size increases, the standard error decreases. This means that larger samples give us more precise estimates of the population mean. Let us look at a concrete example. Suppose the mean height in our study is about 130 centimeters, and the standard deviation is about 4.9 centimeters. This standard deviation reflects a relatively large difference between individuals. Some people are shorter, some are taller. If our sample size is 5, the standard error is 4.9 divided by the square root of 5, which is about 2.19 centimeters. This tells us that if we randomly select 5 people, the sample mean can easily move a couple of centimeters away from the true population mean. Now notice how the picture changed as the sample size grows. When the sample size increases to 20, the standard error becomes much smaller, around 0.89 centimeters. When the sample size reaches 100, the standard error drops to about 0.49 centimeters. At that point, almost all sample means are very tightly clustered around 130 centimeters. This shows us 3 different layers of variability. The mean of about 130 centimeters represents the center of the sampling distribution and closely matches the population mean. The standard deviation of about 4.9 centimeters represents how much individuals differ from each other, which is relatively large. The standard error, which might be 2.19 or even smaller, represents how much the sample mean differs from the population mean, which is much smaller. Mathematically, this explains why averaging is so powerful. By taking averages, we cancel out random individual extremes. As a result, our estimate of the population mean becomes much more precise. In summary, because the sampling distribution exists, we know that sample means always fluctuate around the population mean. By increasing the sample size, we shrink the standard error and make this fluctuation very small. This is why, with a sufficiently large sample, we can be very confident that the sample mean we observe is very close to the true population value. In statistics, one very practical way to understand the sampling distribution of a statistic is called bootstrapping. The key idea is simple. Instead of repeatedly sampling from the entire population, which is usually impossible, we reuse the data we already have and treat it as if it were the population. By resampling from our original sample many times, we can approximate how a statistic behaves across repeated samples. Let me walk you through the bootstrapping process step by step. First, we start with our original dataset. Suppose we have a sample with n observations. This sample could be heights, sales amounts, loan values, or any other numerical data. This is the only data we have, and bootstrapping assumes this sample reasonably represents the population. Next comes the key step, which is resampling with replacement. We randomly draw n observations from the original sample, but we allow the same observation to be selected more than once. Because we are sampling with replacement, some data points may appear multiple times in the new dataset, while others may not appear at all. This new dataset is called a bootstrap sample, and it has the same size as the original sample. After creating one bootstrap sample, we calculate the statistic we care about. This could be the mean, the median, the standard deviation, or even a model coefficient. We record this single value. At this point, we have one bootstrap estimate. Then we repeat this entire process many times. Each time, we create a new bootstrap sample by resampling with replacement, and each time we calculate the same statistic. In practice, this repetition is done hundreds or thousands of times, often 1,000 or even 10,000 times using a computer. Once all repetitions are complete, we end up with a collection of many statistic values. These values form what we call the bootstrap distribution. This distribution shows us how the statistic varies due to random sampling. Finally, we use this bootstrap distribution to make statistical inference. Most commonly, we use it to estimate the standard error of the statistic, which tells us how much the statistic would fluctuate from sample to sample. We can also use it to construct confidence intervals or assess the stability of a model estimate. In short, bootstrapping lets us understand uncertainty using only the data we already have. By repeatedly resampling and recalculating, we can approximate a sampling distribution without making strong assumptions about the population. This is why bootstrap methods are widely used in modern data analysis. Let's see how we implement the bootstrap approach in Python and how to interpret the results. First, Python does not have a built-in bootstrap function in the major packages, so we use the resampling function from the scikit-learn library. This function allows us to randomly sample from an existing data set with replacement, which is exactly what Bootstrap requires. We start by importing the resample function from sklearn.utils. Then we load the loans income data from the CSV file into a data frame called loans income, which you can download from Canvas. Calling head lets us quickly confirm that the data has been loaded correctly. Next, we begin the bootstrap process, and we first create an empty list called results. This list will store the mean from each bootstrap sample. Then we use a for loop that runs 1,000 times. Each loop represents one bootstrap sample. Inside the loop, we call the resample function on the loans income data frame. This creates a new data set of the same size as the original, sampled with replacement. That means some rows may appear more than once, and some rows may not appear at all. After creating the bootstrap sample, we calculate its mean using the mean method. This mean value is then added to the results list. By the end of the loop, the results list contains 1,000 sample means. Once the loop finishes, we convert the results list into a pandas data frame called results table. Each row in this table represents the mean from one bootstrap sample. This table is our empirical sampling distribution of the mean. Next, we visualize this sampling distribution. We first plot a histogram of the results table with 100 bins. Setting density to true normalizes the histogram, so the total area equals 1, which makes it easier to compare with the probability distribution. Then we overlay a density curve on top of the histogram. This smooth curve helps us see the overall shape of the distribution more clearly. Both plots are drawn on the same figure, so we can compare them directly. After that, we calculate two important values from the bootstrap distribution. We compute the mean of the bootstrap means, which estimates the population mean. We also compute the standard deviation of the bootstrap means, which is the standard error. In this tab, we use alloc because of what the mean function returns in pandas. When we call result_table.mean, pandas does not give us a single number. Instead, it returns a series that contains the mean for each column in the table. Even if the table has only one numeric column, the output is still a series, not a single value. Because of that, we need a way to extract the actual number from this series. That is where alloc comes in. The alloc method selects values based on their position. When we write alloc 0, we are simply saying, give me the first value in the series. So alloc 0 means the first element, not a column name, and not a label, just the first value by position. This turns the result from a series into a single numeric value. If we do not use alloc, the variable mean would store a series instead of a number. that can cause problems later when we try to use this value in calculations, formulas, or when displaying results. By using log 0, we make sure that mean is a single number, which is exactly what we need. We then create a text label that displays the mean and the standard error, rounded to 2 decimal places. The letter F before the quotation marks means this is an F string in Python. An F string allows us to directly insert variable values into a text string. Instead of combining text and numbers manually, Python fills in the values for us. Inside the curly brackets, we see min:2f, and this is called a format specifier. The .2f tells Python to keep only 2 digits after the decimal point and to display the number as a floating point value. For example, if the mean were 68,759.9876, it would be shown as 68,759.98, and this makes the output cleaner and easier to read. The same formatting rule is applied to std, which represents the standard error. Again, .2f ensures that only 2 decimal places are displayed. The \n inside the string represents a new line. It tells Python to move to the next line when displaying the text. So instead of showing everything on one long line, the output will display mean on the first line and std error on the second line. As a result, label_text becomes a neatly formatted 2-line message that shows the mean and the standard error, both rounded to 2 decimal places. And this kind of formatting is especially useful when adding labels to plots or presenting statistical results clearly and professionally. This label is placed in the top right corner of the plot so it does not block the data. First, we use the function put.text. This function allows us to write custom text at a specific location on a plot. The first 2 numbers, 0.95 and 0.95, define the position of the text. These numbers are not data values from the chart. Instead, they represent a relative position within the plot area. 0 means the far left or bottom, and 1 means the far right or top. So 0.95 places the text very close to the top right corner. Next, label_text is the actual content we want to display. This is the string we created earlier that contains the mean and the standard error. Then we see transform equals plt.gca.transacts. This part is very important. It tells Python how to interpret the coordinates we just gave. By using transaxes, we are saying that the coordinates are based on the plot's axis system, not the data values. In other words, 0 to 1 always maps to the plot area, regardless of the scale of the data. And this is why the label stays in the top right corner even if the data changes. The parameter HA equals right controls horizontal alignment. It means the text is aligned to the right edge of the text box, so the text grows leftward from the point we specified instead of pushing outside the plot. Similarly, VA equals top controls a vertical alignment. It aligns the text to the top of the text box so the text drops downward from that point. Putting everything together, this line places the label text neatly in the top right corner of the plot, aligned in a clean way and positioned using relative coordinates so it does not overlap with the data or move unpredictably when the plot changes. Finally, we add axis labels and a title to clearly explain what the chart shows. We also remove grid lines to keep the visualization clean. In summary, this code uses the bootstrap method to simulate the sampling distribution of the mean. By repeatedly resampling the data and recalculating the mean, we can estimate both the population mean and its standard error without relying on strong distribution assumptions. This is one of the key strengths of the bootstrap approach. When we look at the chart, we can see that most of the sample means fall inside a shaded gray area. About 95% of the sample means are inside this range. What this tells us is that if we repeat the same sampling process again and again, about 95% of the time, the true population mean will fall inside this range. This range is what we call a 95% confidence interval. A confidence interval is a range of values that we use to estimate an unknown population parameter, such as a population mean. Instead of giving just one number, which is called a point estimate, a confidence interval gives us a range. This is important because real data always contains uncertainty. People naturally prefer clear answers, so they often trust a single number too much. Confidence intervals help us be more honest about uncertainty by showing how much the estimate can reasonably vary. When we say 95% confidence interval, it does not mean there is a 95% chance that the true mean is inside this one specific interval. Instead, it means that if we repeat the entire sampling process many times, about 95% of the intervals we calculate will contain the true population mean. So the confidence level describes the reliability of the method, not the probability of the parameter itself. Let us look at our loan income example. From the bootstrap sampling distribution, the mean of the sample means is 68,759.98. The standard error is 149.08. To calculate the margin of error for a 95% confidence interval, we multiply the standard error by 1.96. This gives us a margin of error of about 292.2. So the confidence interval is the sample mean plus or minus the margin of error. That gives us a range from 68,467.80 to 69,052.18. This means we are 95% confident that the true average loan income for the population lies somewhere within this range. Again, this confidence comes from the method, not from a probability statement about the population meeting itself. To add the mean line and 95% confidence range in Python, we can do this. First, the goal here is to visually show two important statistic ideas on the plot, where the mean is and where the 95% confidence interval lies. To do this, we do not need to rewrite everything from scratch. We simply build on the code we already used to plot the distribution of sample means. Before adding the new features, we need one extra library. We import the stats module from SciPy. This library gives us access to statistical functions, including tools for working with the normal distribution. After adding this import line, it is important to run the cell so Python knows this library is available. Next, we calculate the confidence interval. We use stats.norm.interval. The first argument, 0.95, represents the confidence level, meaning 95%. The log argument is the mean of the distribution, and the scale argument is the standard error. This function returns two numbers, the lower bound and the upper bound of the confidence interval. These values define the range where we expect the true mean to fall most of the time. Then we update the label text that will be displayed on the plot. In this string, we include three pieces of information: the mean, the standard error, and the confidence interval. The .2f formatting keeps all numbers rounded to 2 decimal places, which makes the label easier to read. The \n creates a line break, so each value appears on its own line inside the label. After that, we add a vertical line to represent the mean. We use plot.exaValue and pass in the mean value. This draws a straight vertical line at the position of the mean on the x-axis. And we choose a red color, a dashed line style, and a slightly thicker width. so the line clearly stands out from the rest of the plot. Next, we add the shaded confidence interval. We use penalty dot xvspan, which fills the area between two x values. We pass in the lower and upper bounds of the confidence interval, and this creates a shaded band across the plot, showing the range that covers 95% of the sampling distribution. The gray color and the partial transparency make sure the shading highlights the interval without hiding the data underneath. Finally, we update the title of the chart to make it clear what the viewer is seeing. By changing the title to Distribution of Means with Confidence Interval, we clearly communicate that the plot now shows both the sampling distribution and the statistical uncertainty around the mean. Together, these small additions transform a simple histogram into a much more informative visualization. The mean line shows the center of the distribution, and the shaded region visually explains what a 95% confidence interval really looks like. You don't need to worry about whether your mean is different from mine, because this mean is calculated from 1,000 randomly generated samples. These samples are different every time, so the mean value and the standard deviation would be different too. But the difference is not huge, so they are similar. Here's another example. Imagine an instructor analyzing final exam scores for a course. A 99% confidence interval might say that the true average score lies between 85 and 95. A 95% confidence interval might narrow that range to between 87 and 93. A 90% confidence interval might narrow it even more, say between 89 and 91. As the confidence level decreases, the interval becomes narrower. As the confidence level increases, the interval becomes wider. This shows the trade-off between confidence and precision. In general, a confidence interval for a population mean is calculated as the sample mean plus or minus the margin of error. The margin of error depends on two things. First, the standard error, which tells us how much the sample mean varies from sample to sample. Second, a critical value, which depends on the confidence level and the shape of the sampling distribution. For example, 1.96 is the critical value commonly used for a 95% confidence level when the sampling distribution follows a normal pattern. Next, we will talk about why this critical value comes from the normal distribution and why the normal distribution plays such a central role in confidence intervals and statistical inference. Now that we understand confidence intervals, we need to talk about an important assumption behind the formula we just used. The confidence interval formula we discussed works correctly when the sampling distribution follows a normal distribution. The normal distribution, also called the Gaussian distribution, is one of the most important ideas in statistics and data science. At this point, an important question comes up. Why is the sampling distribution normal even if the original data may not be perfectly normal? This is where one of the most powerful ideas in statistics appears, called the central limit theorem. The central limit theorem tells us that as we increase the number of samples, the distribution of sample means will become more and more normal. And this happens regardless of the shape of the original population distribution, as long as the sample size is reasonably large. In other words, even if the raw data are skewed or uneven, the histogram of sample means will smooth out into a perfect bell curve as we take more samples. This is exactly what we observe in practice. When we generate many bootstrap samples and plot their means, the histogram starts to look smooth, symmetric, and bell-shaped. This normal curve is not describing individual loan incomes. Instead, it describes how the means of samples behave. The mean of a normal distribution can take on any numerical value. negative, 0, or positive. For example, three normal distributions with the same standard deviation may differ only in their means, such as mu is negative 10, 0, and 20. In this case, the curves have identical shapes, but are centered at different locations along the horizontal axis. The shape of the normal distribution looks like a bell. That is why it is often called a bell curve. The width of this bell is controlled by the standard deviation. When the standard deviation is large, the curve becomes wider and flatter, meaning the data are more spread out. When the standard deviation is small, the curve becomes narrower and taller, meaning the data are tightly clustered around the mean. In statistics, we use a special notation to describe a normal distribution. We say a random variable x follows a normal distribution with a mean and a standard deviation. We write this as x follows a normal distribution with mean mu and a standard deviation sigma. This notation simply tells us where the center of the distribution is and how spread out it is. Now let us connect this idea to our practical example. Earlier, we created a sampling distribution of the mean for low income using the bootstrap method. From that distribution, we calculated two key values. The mean of the sampling distribution was 68,759.98, and the standard error was 149.08. Because this sampling distribution is approximately normal, we can describe it by saying that the sample mean follows a normal distribution with mean 68,759.98 and the standard deviation 149.08. In summary, the normal distribution gives us a mathematical foundation for confidence intervals. The central limit theorem explains why the sampling distribution of the mean becomes normal. This is why the normal distribution plays such a central role in confidence intervals. Together, these ideas allow us to move from raw data to reliable statistical conclusions about the population. A standard normal distribution is a special type of normal distribution where the mean is 0 and the standard deviation is 1. Instead of measuring values in their original units, like dollars or centimeters, we measure how many standard deviations away from the mean A value is. This makes different data on the same scale, which makes analysis, comparison, and interpretation much easier and more meaningful. To convert a value into the standard scale, we calculate something called a z-score. The formula is simple. You take the original value, subtract the mean, and then divide by the standard deviation. In words, the z-score equals x minus the mean, divided by the standard deviation. After this transformation, all z-scores together form a dataset with an average of 0 and a standard deviation of 1. In our example with low income, we already created a sampling distribution of the mean using bootstrapping. That distribution has a mean of 68,759.98 and a standard error of 149.08. When we standardize those sample means using the z-score formula, we convert them into values that follow a standard normal distribution. Let's see how to do this in Python. First, we calculate the z-score for each observation in the results underscore table. We do this by taking each value of x, subtracting the mean of x, and then dividing by the standard deviation of x. In Python, this is written here. The z-score tells us how many standard deviations a value is away from the mean. Positive values are above the mean, and negative values are below. Once calculated, we can check the first few rows using results underscore table head to make sure our values look correct. Next, we visualize the distribution of z-scores using a histogram. The command PLT height results underscore table z underscore score beans as 30, edge color as black creates a histogram with 30 beans and black edges for clarity. We change the bins to 30 for desired granularity. We then add labels for the x-axis, y-axis, and a title. This helps us see the spread and the shape of the z-scores. When we plot the histogram of these z-scores, we see blue bars showing the frequency of the standardized values. On top of that, we draw an orange smooth curve, which represents the theoretical standard normal distribution with mean 0 and a standard deviation 1. This curve shows how probabilities are distributed across z-scores. To achieve this, we plot the distribution with density set to true and then overlay a kernel density estimate using a legend as false. This gives us a smooth curve that shows the probability density. Remember here, the bins is 100. Be careful, the way to set the histogram and distribution is a little bit different here. The first line uses matplotlib directly. When I say polity.heist, I mean I am calling the histogram function from matplotlib. This line is very straightforward and is commonly used when you are working directly with matplotlib and want full control over the plot later. The second line uses pandas plotting instead of matplotlib directly. When I say result table.z_score.plot.heist, I am asking pandas to create a histogram from that column. Pandas is actually using matplotlib behind the scenes, but it wraps it in a simpler interface. The important difference is that this line returns an axis object, which I store in a variable called x_z. This makes it easier to customize the plot afterwards, such as adding labels, titles, or annotations. So in summary, the second line is pandas-based, more convenient, and it gives you an axis object that is easier to build on for more advanced plotting. We also draw two vertical reference lines. But before we do so, we need to calculate the mean and standard deviation of these z-scores, as well as the 95% confidence interval for the z-scores. We use that norm interval function with 0.95, z-score, mean and standard deviation, which returns the lower and upper bounds of the confidence interval. This interval represents where 95% of the z-scores are expected to fall, assuming a normal distribution. Then we can draw two colorful lines. The first vertical line is placed at the lower bound of the confidence interval. We access this value by using confidence interval z with square bracket 0, which means the first value in the confidence interval array. The color is set to green, the line style is dashed, the line width is 2, and the label text says CY lower followed by the value formatted to 2 decimal places. The .2f means we keep only 2 digits after the decimal point, making the number cleaner and easier to read. The second vertical line works the same way, but it uses confidence interval z with square bracket 1, which refers to the upper bound of the confidence interval. This line is colored blue, uses the same dashed style and width, and the label text says C1 upper, with the value again rounded to 2 decimal places. Together, these two lines visually show the range where we believe the true mean is likely to fall. Here is a little bug. I misspelled the result table with an additionals. Just need to delete it and we're good. As the result, the green line is at negative 1.96 and the blue line is at a positive 1.96. These two values define a 95% confidence interval in the standard normal distribution. Everything between negative 1.96 and positive 1.96 covers 95% of the total area under the curve. We also use plt.xlim to set the limits of the x-axis. By passing -4 and 4, we force the horizontal axis to only show values between -4 and +4. This helps keep the plot focused and prevents extreme values from stretching the chart and making the main data harder to see. At the end, we print the mean of the z-scores, the standard deviation, and the confidence interval. This allows us to confirm that the mean is around 0, the standard deviation is close to 1, and the 95% confidence interval captures most of the data. Only 2.5% of the data lies below -1.96. This is the small left tail of the curve to the left of the green line. That means 97.5% of the data lies above -1.96. Similarly, only 2.5% of the data lies above +1.96, which is the small right tail of the curve. The remaining 97.5% lies below that value. This is why we use plus or -1.96 for a 95% confidence interval. The middle 95% of the data is considered typical, while the 5% outside, split evenly into two tails, represents extreme or unlikely values. Lastly, we add the labels and title to this distribution chart. Now, some of you might be curious why 1.96 is the z-score, or critical value for 95%, because there is a z-score table we can refer to. Now let's walk through several normal distribution and z-score questions. For each question, I will first explain how we solve it conceptually in statistics, and then I will explain how we translate that exact logic into Python code. Let's start with the first setup. We are given a normal distribution with a mean of 50 and a standard deviation of 10. These two numbers describe the center and the spread of the distribution, and we will use them repeatedly. The first question asks, what is the value of x when the z-score is 1.4? From statistics, we know that a z-score tells us how many standard deviations a value is away from the mean. To go from a z-score back to an x value, we use the formula x equals the mean plus the z-score times the standard deviation. So we take 1.4, multiply it by 10, and then add 50. This gives us the x value. In Python, we do the exact same thing. We first store the mean as 50 and the standard deviation as 10. Then we store the z-score as 1.4. Finally, we calculate x by adding the mean to the product of the z-score and the standard deviation. And we print the result. The second question reverses the process. This time, we are given an x value of 30, and we want to find the z-score. Statistically, the z-score is calculated by subtracting the mean from x and then dividing by the standard deviation. Since 30 is well below the mean of 50, we expect the z-score to be negative. In Python, we follow the same formula. We subtract the mean from 30, divide by 10, store the result as a z-score, and print it. This tells us exactly how far 30 is from the mean in standard deviation units. Next, we move on to probability questions using IQ scores. These scores follow a normal distribution with a mean of 100 and a standard deviation of 15. The first probability question asks, what is the probability that x is less than 80? Statistically, The first step is always to convert x into a z-score. We subtract 100 from 80 and divide by 15. Once we have the z-score, we look it up in the standard normal table to find the probability to the left of that value. In Python, instead of using a table, we use the cumulative distribution function from the SciPy stats library. After calculating the z-score, we pass it into this function. Which directly returns the probability that x is less than 80. The next question asks, what is the probability that x is greater than 136? Again, we start by converting 136 into a z-score by subtracting the mean and dividing by the standard deviation. The standard normal table gives probabilities to the left. So to get the probability of being greater, we subtract that value from 1. In Python, we do exactly the same thing. We calculate the z-score, use the cumulative distribution function to get the probability to the left, and then subtract that result from 1 to get the upper tail probability. The next question asks for the probability that x falls between 95 and 110. Statistically, we calculate the z-score for 95 and the z-score for 110. Then we find the probability less than each value using the z-table. The probability between them is the larger probability minus the smaller one. In Python, we compute both z-scores. Use the cumulative distribution function to get both probabilities and subtract them. And this gives us the probability of being between 95 and 110. Next, we are asked to find the IQ score that corresponds to the 90th percentile. Conceptually, this means we want the value where 90% of the distribution lies below it. Using a z-table, we look for a probability close to 0.9 and then convert that z-score back into an x value using the mean and standard deviation. In Python, this is much faster. We use the percent point function, which does the reverse of the cumulative distribution function. We give it the percentile along with the mean and standard deviation. And it directly returns the corresponding x value. Finally, we are asked to find the middle 30% of IQ scores. The middle 30% means values between the 35th percentile and the 65th percentile. Statistically, we find the z-scores for these two percentiles and then convert both back into x values. In Python, we again use the percent point function to find the two z-scores. Then we multiply each z-score by the standard deviation and add the mean to get the lower and upper bounds of the middle 30%. This is what we can do on normal distribution in Python. It is important to understand the mean, standard deviation, and probability in normal distribution. We will learn deeper in coming class to use this information, help us understand the relationship between different variables. Now, it is time to you to do the quiz and assignment to check your knowledge of this section.